What do you say? You what? Yeah, we could add one question just for us. Why don't we make one up? Huh? Okay. Well, all right, let's get started. So I know our heads are spinning with operation amplifiers and negative feedback. I just realized this negative feedback has really a terrible connotation, right? But negative feedback can be good. Most of the time we want positive feedback. But with op amps, very often we want negative feedback. Anyways, let's take a break, okay? We'll talk about something totally different. Let's enjoy this. So this totally different thing that we are going to talk about are capacitors. So why we're going to talk about those? Well, while learning for the midterm, sorry, I already get back there, right? While learning for the midterm, you certainly found that there are lots of things that you can do now that a month ago you didn't know how to do, maybe you didn't even try to do, right? So I think you've learned a lot, and I hope you agree with me about that. Especially we worked on these sensor interfaces, right? We hook up some kind of a device to an electronic circuit, and then we can measure light, temperature, humidity, we can amplify sound, and so on and so forth. Okay, so those are all great things that we can do. But there are also a lot of things that actually we cannot do. And I've listed a few of these things here. Like a timer circuit. If you wanted to build a simple light timer in a staircase or so, you press a button, the light goes on, and then after a minute or so, the light automatically turns off to conserve energy, of course, or so. We couldn't build that out of operation amplifiers and resistors, just like that. The circuit ideas that we have so far, the circuit concept we have so far learned about, we couldn't do. We couldn't build a staircase timer. We couldn't build a voltage doubler, right? If we have a battery, and out of the battery, a lithium battery, maybe it's about 3 volts comes out, we actually need twice the voltage or so. There's no way we can do that with resistors, right? Of course, we could use an operation amplifier and amplify the voltage from the battery, but why wouldn't that actually solve our problem? Yeah.
The source for the operational amplifier would need to be at least the amount.
Exactly. We need a supply for the operation amplifier that is at least 6 volts if we want to get 6 volts, right? And so we kind of build a recursive problem, and we wouldn't know how to do that yet. There are also things that we just can't explain, like the circuits. So far, we never talked about that the speed that it takes or the time it takes a circuit to actually compute or provide its output. We haven't talked about that, and we sort of ignored this. But of course, in reality, we know that circuits, they have absolutely finite speed, and why in the world is that? One idea, obviously, is the speed of light, but it turns out most of the time circuits are actually a lot slower than they could be if we just looked at speed of light. And then any kind of memory, right? Memory is important. You have to memorize a few things, not a whole lot, but a few things for the midterm. Memory is important, and we wouldn't know how to do that out of resistors. Well, actually, that positive feedback operation amplifier actually turns out to be a memory, but we haven't really looked at it like that. So, anyways, we need some form of efficient memory in order to do many additional and all these things that we just talked about. Okay, so how could we build memory with electronics? Well, it turns out that there are lots of ways to do that, but however, with slicings, in a way, they always tie back to electrons. Right? Electronic circuits, of course, they work on the basis of electrons, and hey, if we somehow could store a number of electrons, well, we would have memory, right? Have we stored 100 electrons or 1,000 electrons or whatnot? Okay, so let's look a little bit more at electrons. Here what I've shown are 2 pieces of metal, so they're conductors, and they're made out of atoms, of course. What are atoms? How do they sort of look like? A very simple chemist kind of view of atoms, or maybe physicist. What's an atom made out of? Yeah. Okay, I didn't quite hear, but I assume you said there is a nucleus that consists of a number of protons. They're all positively charged. And then surrounding that nucleus, we have electrons, and they're negatively charged. And what's the difference? between the number of protons and electrons in an atom? It's 0, right? Normally it's 0. Normally there is the same number of electrons and the same number of protons in the atom. And there are some other components that we don't need to worry about here. But now if we have a conductor, what happens to the electrons? Well, in a conductor, the outermost electrons, one or two outermost electrons, we can sort of think about that like a nut, right? There is inside there is the core, that's the protons, and they're very, very much stuck there, right? We would have to use nuclear, what is it called, breaking them up. So we certainly don't want to get into that, right? So the nucleus is absolutely fixed. Those are whatever 12 protons, then it would be carbon, isn't it? Whatever, right? So we have in the center we have that nucleus, and then surrounding it we have a sort of a cloud of electrons. And these electrons, they all move a little bit around, and the outermost electrons in a conductor, in a metal, they're actually free to take off and go somewhere else. Okay, so what I've shown here are just the outermost electrons here, these minus signs, and then I also draw the corresponding plus sign. Okay, so every electron, of course, is balanced by a proton, otherwise the atom would not be charge neutral. So I've shown the plus signs. They signify the protons that correspond to those electrons, and I've shown only those electrons that are actually free to move around. Okay? And so the plus signs, they will never move around, but the electrons, conceivably, they could move around. So why would they move around? Well, for example, we could apply a voltage across this entire construct. Now, if let's say we applied here plus minus 5 volts or so, then charge would want to flow, right? That's the job of the voltage source. And now, because these are electrons that are flowing, they actually go against the voltage, right? Because they're negatively charged. Okay, so don't worry too much about that direction, but happens to be this way. So how this is going to look like, the situation now? Well, these two electrons, they took off from here and they ended up down here, right? Suddenly we have two electrons missing in the top, in that top chunk of metal, and we have two additional electrons in the bottom part of it. Consequently, what's the charge? What's the total charge in the top plate now? Well, it's actually written there, right? It's only plus 2 electronic charges. Why? Well, because we still have the protons. They're still there, and they're positively charged. They cannot move around. Okay, but the two electrons, they've taken off, so two charges are missing. There are now suddenly two more positive ones than negative ones. Consequently, totally, we have two electron charges, positive, electron taken positive. We have two more in the top plate. And where did they go? Well, they went to the other plate here. Here, suddenly we have 4 protons, but we have now 6 electrons, and so altogether we have a negative charge there. Notice that the charge neutrality still holds for this entire device. Of course, it doesn't hold for one of these plates alone, but for the entire plate, what's the total charge on this thing? 0, right? So charge conservation still holds. It's just we sort of, inside this device that consists of 2 chunks of metal, inside the device, we somehow separated the charges. But we didn't create new ones, and we didn't destroy any ones. Okay? So now this thing is actually, this construct is called a capacitor, and it's very useful. It really is exactly what we want to do, right? It's kind of a bucket for electrons. Sure, the electrons were there before, but we sort of can split them. We can say go on this plate or go on that plate, and all we need to do is apply some voltage to it or something like that. Okay, so now we can define something like Ohm's law, but for capacitors. It turns out that for such constructs, for good ones, there is a linear relationship between that charge split, right, between the amount of charge that is on one plate and not on the other, and the voltage that we apply. And the proportionality constant, this thing here, is called capacitance. Just like in a resistor, we would have that the current is equal to the voltage divided by resistance. Well, here we have that the charge is equal to the capacitance times the voltage. So a very, very similar law. And of course, what is that C? Well, it depends on what kind of a component we get, on how the component is made and whatnot. In fact, there are lots of different, we can buy these things just like resistors. You can go to the electronics store or whatever and buy it on the web. So there are some very small capacitors. There are femtofarad. What's femto? Yeah, 10 to the minus 15. That's how tiny it is. Okay, and on the printed circuit board, what's a printed circuit board? Is that usually green or brown stuff, right? That's in our electronic gadgets where we have all the components soldered to. Just by soldering a component somewhere or so, we typically end up with a capacitance of on the order of picofarad. What's picofarad? Pico? 10 to the minus 12, right? And then there are also, at the other end of the scale, there are supercapacitors. They can be up to tens or even hundreds of farads. So we, of course, could calculate how many electrons there are there on those. So. All right, so this is how these capacitors might look like. Unfortunately, there are many more different versions of capacitors than there are resistors. And the other thing that is even more painful is that for resistors, remember that color code that you used in the lab? It's very systematic, right? If you have a resistor, you can look up, I think in a lab it's somewhere hanging on the wall, right? There's this color code and you can figure out the value. Unfortunately, it's not nearly as organized for capacitors. So it's often much harder to figure out what the value of a capacitor is. But anyways, these are pictures of some capacitors. Yeah, it's written in some way on it, but I keep forgetting how it is because it's really a tricky thing. Like 10, 5 or something like that which would be something like 10 to the 5th. I've forgotten even what it is. I mean, all I tell you that it's a little bit trickier, and yes, in the lab, obviously we will help you to figure out what the value is, and when you need a certain capacitor, make sure that you can get that. Okay? So they're also very big capacitors, and those are usually so-called electrolytic capacitors. There is some chemistry going inside to be able to store an incredibly large amount of charge. And I just want to point out something, and that actually says it here, beware of polarity. If you look at these capacitors very carefully, then you will see actually here, these. Here it shows minus signs, and if you were to turn it around on the other side, it would show plus signs. So you have to hook those up correctly. You have to make sure that the one end is always more negative than the other, and just be very careful. What happens if you hook them up the wrong way? Yeah, they actually explode. Okay, and it makes a mess. I don't know. In fact, I don't know exactly what happens because it has never happened to me in the lab. I must be a very careful experimenter, but the TAs have told me that it happens every year. A few people, they explode their capacitors, so make sure that you're not the one. All right? So, so far nobody has gotten hurt, so I didn't look into any details in it, but obviously be a little bit careful. What happened here? Well, somehow this decided to go sweep down a little bit. But anyway, so we have that top law that we talked about. That's kind of Ohm's law for capacitors. Now, there is something a little funny about that. Instead of relating voltage to current or current to voltage, it actually relates charge to voltage, right? But we can fix it very easily. What is current? Well, it's simply the amount of charge that passes per second. So it's dq dt, right? And so if we take the derivative on either side of this equation, we get dq dt, that's simply the current, and that is equal to capacitance times the change of voltage, okay? Now, there is something, so this of course assumes that for any mathematician here, this assumes that the capacitance is not a function of time, which usually if you just buy a fixed capacitor, of course, is true. Now, there is something quite remarkably different from the normal Ohm's law that we are used to, that I equals V over R, right? here we have I equals C times dV dt. What's so different here? Doesn't bother you at all? Yeah, exactly. Suddenly we have actually a differential equation. We no longer have an algebraic equation, we actually have a differential equation. Kind of makes sense, right? If we want to involve memory, there should be time in there. Well, and it turns out that that's captured with the differential equation. So, sort of a price that we have to pay for this new functionalities that suddenly we will have to deal with differential equations. So we will do that in due time, but first we will look actually just a little bit at charge. It turns out that by just looking at charge and not looking at the differential equation at all, we actually can do a lot of very interesting things. So, but one of the things, let's look here. What is the power delivered to a capacitor? So let's look at the circuit. Here we have a current source, we have a capacitor, and the current source forces a current into the capacitor. What's going to happen in that case? Well, basically charges, they take off here, they go in this direction, and then they end up on the other plate. Now, if it's electrons, they actually run the other way around, right? And so most likely it's going to be electrons. But basically, it actually is going to exactly do this charge separation. And now and here we need to look at the differential equation. Right? We have I equals dq dt. If I is constant, then integrating this is very simple. Then Q is simply equal to I times T. So because I is I1 and is constant, this is simply going to be a ramp. That's the charge stored on the capacitor. Okay? And now we can also figure out what is the voltage on the capacitor. Well, we had Q equals the capacitance times the voltage, and consequently, we can solve for the voltage on the capacitor. That is equal to QC divided by capacitance. So there would be another line. The slope depends on the value of C. That would be VC. Okay? So now what's the power? Well, the power is not quite here. But what's the power defined as? What's the power defined? What's the definition? Yes. Yeah, it's simply current times voltage. That always applies. So that you knew already, right? That could even be on the midterm. But power is the current times the voltage. So that's written already here. That's I1 times. But what is the voltage? Well, that happens to be I1 times T over. It's the charge over capacitance, and the charge is I times T, which is calculated. So the power is actually I squared T over C. Okay? And so it's not quite, did I put the square here? I square, I1 square. So it actually is going to look something like this. Well, it's a quadratic, proportional to, oh no, as a function of time, that's not true. As a function of time, it's still going to look like this. Forget this guy, huh? All right? So that's the power. Oops. The power. Okay, so power is actually delivered to our capacitor. In this circuit, the current source, not surprising, hey, it's a source, it delivers power to this capacitor. So question, what's going to happen to this power? Exactly, it's stored in the capacitor, right? All these charges, they're separated, they're stored in the capacitor. At some point, we can take this power back out. In fact, the capacitor, we can use it just like a battery. And that's very important to realize. Capacitors, at least ideal ones like here, they do not dissipate power. They can store power, they can absorb it, store it, and then they later give it back. Okay? So in that case, of course, we can ask ourselves, well, what's the amount of energy that we're storing on one of these capacitors, right? And so that's the next slide that goes and looks at that. Well, energy again, and that's sort of from way back, either in physics or in the first one or two lectures in EE40. Energy is simply the power integrated over time, right? That's what we pay to the electricity company. We are not paying for the power, we are paying for how long we are actually using this amount of power, right? Okay, and so we can do this integration here, and I've shown that here already, and we get what is put into the red box, the energy that's stored on the capacitor is 1/2 the capacitance times the voltage across the capacitor squared. Okay? Okay, and capacitors do not dissipate the power, they just store the energy. All right, so we can go through a very simple example here. Suppose that we had a supercapacitor and the value was 30 farads. So they exist. And let's then suppose that we charge this supercapacitor to 5 volts. How much energy have we stored on this supercapacitor? How would you figure that out? Yeah.
The half capacitance voltage squared.
Yeah, exactly. 1/2 CV squared. C is given 30, V is given 5. So 1/2 C, that would be 15 farads times V squared, 25 volts. So 15 times 25 volts squared is 375. Wow, you're good. So 375, that's actually true. I calculated before then, because when I'm standing here, I couldn't do 1 + 1. Okay, so is that a lot of energy? Well, the best way to figure that out is to put it in perspective, right? I put here a picture of an alkaline battery. This alkaline battery, when it comes fresh off the store shelf, has about 10,000 joule. So it's not it's not an enormous amount of energy. But now let's ask ourselves what we could do with this energy. Okay, maybe that's another way to look at it. Well, if we want to do something with the energy, well, we, for example, Annie has one of these toy helicopters. So they very often, you have to connect them to a battery, and then afterwards they start. What they actually have inside is a supercapacitor. They very quickly transfer the energy from a real battery, for example, an alkaline cell, into that supercapacitor, and then it takes off and flies off the supercapacitor. It's the energy that's off the supercapacitor. Suppose that this little helicopter, whatever it happens to be, takes 0.5 amp of current. How long could it run? Well, first of all, there is something that we have to look at, and that is, as we are drawing current out of the capacitor, what's going to happen to the capacitor voltage? Exactly, it just linearly decreases. If the current is constant, well then the voltage across the capacitor linearly decreases. With a battery, is that also the case? Yeah, it's most batteries, it's not the case, right? You use a battery, and only when it gets very close to the end of its life, then the voltage starts dropping. So as a function of time, if you draw a fixed current, a capacitor, function of time, here's the voltage, and the voltage of a capacitor is simply going to look like this, whereas the voltage of a battery is going to look something like this. Okay? So because of this, we cannot quite get all the energy out of the capacitor, because what happens if the voltage keeps dropping? Well, at some point we have some kind of a minimum operating voltage that doesn't turn the thing is on the helicopter strong enough anymore, and the thing just comes down, right? So let's suppose that the minimum operating voltage was 3 volts. How much energy is actually available from our capacitor in that case? Well, we start out at 5 volts, and then and there we have actually, what was it, 375 joules energy. At the end, we end up at 3 volts. 3 volts. How much energy do we have now on the capacitor? So it's 1/2, that's 15 times 9, 135 joule, and the delta energy is equal to 240 joules. So it's really 240 joules we can use, and the rest stays on that capacitor. We can't use it because the voltage drops too low. We cannot use that energy anymore. It's not going to turn the helicopter's blades. Okay, and so how long is it going to operate off the 240 joules? How would you figure that out? Well, we are drawing half an amp, the energy. Okay, so we would divide the energy by the current. Yes, we need to look at. Let's see. We need to look at the energy. The energy is actually equal to so we can figure out what is the charge, right? What is the charge, and then from that we can find what is the time.
Charge directly from the capacitance and the voltage.
That's right. That's right. We can get the. Let's do that. So the charge is equal to the voltage. That's 2 volts that we are dropping, and times the capacitance. So that is actually 60 Coulomb. And we have to divide this now, Q over I is equal to 60 Coulomb over half an amp. That's 120 seconds, right? So it's 120 seconds. All right. Okay, that's how long we can run this thing off. Thanks a lot. So. All right, so we can use these capacitors to store energy, and then we can use it. And actually, I switched too quickly from this slide. Should we use batteries or should we use capacitors? Well, it turns out if we look at price, batteries are a lot cheaper, and also the volume is smaller for a battery and the weight than for a capacitor of equivalent capacity, energy capacity. But nevertheless, there are big advantages. A battery, if we want to draw current only once in a while, but we want to draw really a lot of current, batteries don't like that. So a good thing about capacitors is that you can leave the charge for a very long time, and then you can draw really a lot of charge, and then you don't use any charge anymore. That's important, for example, in sensor networks. If you listen around in Soda Hall and so on, also in Cori, a lot of people, they do research on sensor network. Put sensors all over, and then we can sense the environment, the temperature and so on, the light and whatnot, or the traffic, and use that information to sort of enhance our lives. Now, one of the challenges in these sensor networks is that every sensor needs some kind of a battery, right? And if you really are successful and have now blasted your entire world with sensors, well, what you have done is you have set yourselves up for a terrible nightmare. Now you have batteries all over in the world, right? And of course, batteries, they run out at some point, and then you go and have to change them. And so you really have a maintenance headache. Instead, one thing you can do is you can use so-called energy scavenging, that you somehow look for a little bit energy that's around in the environment, and you grab that energy and you use that to run your sensor. Any ideas for what kind of energy we could use that would just be around? Yeah?
Just electromagnetic noise.
Electromagnetic noise, yeah. Turns out it's very, very difficult. If you are close to a power wire or so, then you may be able to suck out some energy out of that electromagnetic field. In fact, just yesterday over in Corey Hall, somebody gave a presentation and he built this thing that when you put it next to a wire that carries 50 amps, is that a lot? 50 amps? It's a lot, right? It's a lot. If it carries 50 amps, he got...
Used for maybe 20.
Yeah, yes, 20 probably. Yeah. So he got 17 milliwatts out. 17 milliwatts, is that a lot? Turns out actually it's quite generous. You can run a lot of sensors off of 17 milliwatts. So obviously you can't run a supercomputer or a cooking stove or so off of 17 milliwatts. But electronic systems, there is a lot you can do with 17 milliwatts. Okay, so electromagnetic energy, just scavenging that, it's a possibility. I recently saw a proposal. There was somebody who wants to use the electromagnetic energy that you get from the GPS signal, right? Every year, supposedly, we get GPS, at least outside, right? And we, of course, that's it, a little bit of energy. We could harvest that. Could we do anything with that? Do you think? Do you believe that?
I think it wouldn't be at all efficient. The GPS signals.
Well, okay. Efficiency is the military or the taxpayer pays for the GPS energy. I don't pay for it, so for me it may be efficient. Although I pay taxes, so yeah, I don't like to think about that one. So efficiency. Well, I mean, you get that anyways, right? No, but the amount of energy really would be totally minuscule. I think was a dumb proposal. I wouldn't want that one, but anyway, no, but actually one thing that works very well, you worked on it in the first lab. Light, right? Especially solar energy. Solar energy is something really good to scavenge. So getting back to a capacitor, you can then load that solar energy little by little, right? You let it trickle into a capacitor, and then when you want to make a measurement, you need maybe a lot more current than is available from the sun, especially at night, right? But then you use the energy of the capacitor, and then you fill it up again when there is light. Yes?
Couldn't you just use a rechargeable battery?
You could use a rechargeable battery, but exactly the rechargeable battery would have the sort of the disadvantage that if you want, most rechargeable batteries don't like it if you fill them with very, very small amount of energy over a long time, and then you draw a very large amount of energy during a short time. In fact, I believe that's even a problem also in electric vehicles, because there, if you think about it, they have the same problem. Right? Most of the time, actually, the amount of power that you need from your engine, from your car engine, isn't very high. Right? If you're just cruising, you don't need a lot of power. But when you're starting, you really need a lot of power. That's when you need that 100 horsepower or whatever it happens to be. So in cars, you have the same problem. And they do all sorts of things like running off the battery voltage in cars is often several hundred volts. They stack a lot of batteries in order to address this problem. Anyways, I mean, the point is that capacitors have advantages, they have disadvantages. The disadvantage is that the voltage drops gradually, can't use all the energy. That's better in batteries. Advantage is that you can charge them very, very quickly. In fact, yeah, that's an important thing also. A capacitor you can charge in a minute or so. If you try to do that with the battery gets hot and it will probably explode too, yes. Yes, they do wear out, especially these well, not all of them, but certainly these supercapacitors. Every chemical capacitor, electrolytic capacitor, supercapacitors, they do wear out. In fact, one thing that, so if you have audio system or so, then very often if they are 5 or 10 years old, they start exhibiting a hum or so. It's very often that the capacitors went bad. Okay? If you go and unsolder all the capacitors, replace them by new ones, you fixed your stereo. Yes?
Why is Q equal to 2VC instead of DC?
Oh, that's simply the amount of charge that we actually are using, because we are we're starting at 5 volts and then we end up at 3 volts, so the amount of charge that we actually got out of the thing was proportional capacitance and 2 volts. Okay, good question. Okay, now let's look at a bunch of applications of capacitors. More applications, right? We saw already a capacitor as a battery. Here is another application where really we are using the capacitor as a battery. So the example here is a microprocessor. A microprocessor is just like one of these cursors, so it uses very little energy and then it uses really a lot of energy. Now, obviously, the power supply is hooked up to your microprocessor chip through some kind of a long wire. Okay, I used some kind of a symbol here. Let's not worry too much about that symbol at this point, but it's a long wire. What happens through a long wire, and we have sort of swept that under the rug so far, but actually what happens in a long wire is that it's difficult to get a lot of energy or a lot of current through very quickly. If you can run 20 amps in a long wire and keep it 20 amps for a long time, that's no problem. But you can't, in a long wire, run 0, 0, 0, and then 100 amps, and then 0, 0. It just doesn't want to go up to a high current very quickly. So in microprocessors, that's a problem, because microprocessors, if that thing runs at, for example, 1 gigahertz, then what really happens is if we were to look at the current, I, that's running into our microprocessor function of time, it would look like spikes, and the spikes would be a part, well, what's 1 over a gigahertz? 1 nanosecond, right? There would be spikes of current, spaced by perhaps a nanosecond. They would be very large, and then there would be little current, and then is again once a large spike of current. These spikes of current, they don't go through this long wire, okay? And so how could you fix that? Well, we can replace the long wire by a short wire, and then everything will work fine. But the little problem is that our power supply is big, and we cannot put everything just next to a microprocessor chip. But what we can put there very close is we put there a capacitor. And now what happens is that constant amount of power flows from the supply into the capacitor. It always keeps the capacitor more or less charged, and then bursts of power or current come out of the capacitor and they go into a microprocessor. So, for example, if we had a so if I'm not sure what what we will do here is we will put a few nanofarads of capacitors right next to our microprocessor, and what happens is that the sort of a constant average power flows through our long wire onto that capacitor. All the power really is delivered from our supply, like it should, but then all this bursty current actually flows out of the capacitor into the microprocessor. And if you ever built anything yourselves and looked actually at the data sheet, then you may have seen that the vendor of a part, it could be a microprocessor or something else, usually tells you to not only use their part, but also to put capacitors on various pins, usually supply pins. Anybody has seen that? No? Wow, that's the difference. When I was a student, it was still half of the class was building stuff, and we always were wondering why it wouldn't work and so on, or whether we could get away with not putting these capacitors in. Now I guess the trouble is that the electronic gadgets you can buy are so much better than what you can build that maybe it's not worth it to build it anymore. But yes?
So what happens exactly with a microprocessor? Just the resistance drops and increases for 1 nanosecond? Like, why will it draw so much current at once?
Why the microprocessor draws a very low, why the current from the microprocessor is very spiky? Right. That's the question. Well, that's because of the way it operates. Whenever it gets a clock pulse, Then it does a computation. And we'll see later that actually in order to do a computation, it has to fill a bunch of capacitors. And that needs a needle of current, a spike of current. Yeah.
So if the circuit was supplied for a long time, the capacitor will act like as an open water, right? So
this acts like an open over the short time. And this acts like an open over the capacitor acts like an open over the long time.
Yeah.
But over short time, the capacitor acts like a short with a voltage source in series, very low impedance. Yeah. So time really comes into play here. Let's look at another example. This is a parallel plate capacitor. Let me explain a little bit better what I actually mean with a parallel plate capacitor. These are two plates, this one here, and then there is a second plate at some distance, d or something. Okay, so this is a so-called parallel plate capacitor. So we have two plates of metal. Usually, they are separated by a certain distance. Okay, so this happens to be a capacitor, and we easily can calculate the capacitance. In fact, there are lots of textbooks that explain us what the capacitance is. So this here, this distance, the distance between the capacitor plates is T in this equation. The area, well, that's the area of the plate, of one of the plates, that's A. Okay? So then the capacitance is going to be, well, the larger we make the area, the more capacitance we get. Kind of makes sense, right? If we put the capacitor plates very far apart, well, ultimately they don't interact and we can't store anything there. So it's inversely proportional to T. That makes a lot of sense. Then there is some proportionality constant. So we have to talk about that. So the first one here, that's just a constant, sort of a nature constant, much like Boltzmann constant or whatnot, right? Or like the electronic charge. So that's just a constant. And then the other part is epsilon r. Well, it depends on what material we actually have between these plates. If, for example, we have vacuum, then this epsilon r is equal to 1. But if we have water, and air actually is very close to 1, if the air is not too humid. But if we have water, then this epsilon r is on the order of a whopping 80. Okay? So it varies very much on the material. And I give you another few examples here, even concrete, God knows why. That was somehow, I found this on Wikipedia. So we can use this now. We can use this, for example, to make a fluid sensor. Suppose that you have a tank with water, and you want to know how much water is in the tank. Well, we could build a capacitor, and in the middle of the capacitor, between the plates, what you have is just the water. If you have a lot of water, then the water goes high on it. The water level is high here. This the water level, and if you have less water, then this goes to a lower level, right? And you could figure that out by measuring the capacitance. Yes. Yeah, then it's a little bit different, right? So go to Google and type salt water and capacitance or permittivity or whatever, right? And then you'll. Okay, I don't know exactly. So, Alex, do you know? Yeah, if it's really conductive, then it wouldn't be a capacitor anymore. But you could put a small plastic film between the metal plates and the fluid, and then you could keep that. But there are all sorts of other things happening, like double layers and so on. Don't ask me about that. I'm not a chemist. So some of my students know because they have to fight with this problem to build their things. But let's just use. So what is the capacitance of this thing? Well, the capacitance of this thing is going to be equal to, somehow this is the side A. Then there is the water level W. So the area is actually W times A. And then the distance between the plates, let's call this T again. And then it's going to be equal to epsilon r times epsilon 0. So now, actually this is the there's the capacitance C1 of the part that has fluid in the middle. And then there is also capacitance C2. That's the capacitance of the part that doesn't have fluid there. C2 is equal to epsilon r times epsilon 0 times, let's call this here, let's call the entire thing to be, well, maybe W, capital W. So that we W minus W times A over T. And this one here is 1 air. And this one here is on the order of 80 water. And so you will see that the total capacitance C total is going to be C1 plus C2. That's going to be a function of the fill level W. Okay? So we actually can we can use this very simple thing to make a capacitor, and the value of the capacitor is proportional to the fill level. Any idea where this is used? Do you know any application where this actually is used? For example, water levels. You know what a level is? Usually have these bubbles, right? And if it's horizontal, the bubble is somewhere in the middle, and we can make sure that it's certainly a level was used to build this fluoride to make it nice and horizontal. Okay. Now, if you look more carefully, then you will find in the stores over the last 20 years or so, you find also levels that actually have a digital display. It doesn't only show you when it's horizontal, but it actually shows you the number of degrees of deviation from horizontal. So what it has inside is it simply has two of these basins, and the water goes from one to the other depending on how you tilt it, and then you measure the two capacitors, you compare them, and calculate the angle, and that's what you display. It's exactly the way this is done. And of course, we will need some kind of a circuit that allows us to measure what the value of capacitance is, and we're going to build this next time, but let me just show you a few other applications. The touch sensor is one of them. You're going to build this one in the lab, but if you have one of a smartphone, then of course you know that you can touch the screen and you can move around. Hey, that's a capacitive sensor. So here, if you put your finger on top, the capacitance between these fingers changes, and we can measure that. And you'll do that again in Lab 6. On your smartphone, there is invisible traces, invisible wires on the screen. You can't see them because it's a material that is conductive called ITO, but it's transparent, so you don't see it. And what you're actually doing is you are putting your finger there because your finger is mostly water, right? It changes the capacitance, and then we can detect where your finger is. All right? So another example here, that's actually something we did in our lab. This is an accelerometer. The accelerometer really consists of a mass. When you observe a crash, then the mass, if I was crashing with the car into a wall, then of course the wall would stop the car, but I want to keep going, right, because of inertia. Okay, that's exactly how an accelerometer works. It's just the mass is a small piece of silicon. If this thing crashes into the wall, this piece wants to keep moving. The car stopped by the wall, and consequently, these tines here, these are small conductors. They are stuck, they don't move, but these other ones, they keep moving. The distance changes. Well, that's the distance between two conductors that changes. Well, two conductors close to each other, that's a capacitor. If the distance changes, the capacitance changes. So we can use this to measure acceleration, and that's a circuit that does this. It has all sorts of other electronic components that perform analog digital conversion and so on. So forth. So this would be one of these ICs that we've built in my lab, for example. Okay. So here is a summary, and then, well, this was an introduction, right? So there are not too many skills yet, but you should be able to calculate the charge and energy, and you should be able to calculate the value of capacitance of a parallel plate capacitor. Okay? Good luck on Friday.